Alright, so I'm going to be making a video for, this is a HL question, chapter 5, section 5C, number 2. And it's asking us to draw a Venn diagram and then show the things over on the right. Okay, so I'm going to do my best to do that. Let me preface this by saying that I don't think this is a very well written question because of an issue that comes up here at the end, the fourth thing that we're supposed to show, but I'll go ahead and try to explain as best I can as we go. All right, so here we go. The first thing they want us to show is that A is equal to A and B union A and not B. Okay, so let's find those first. So A and B is the intersection, A intersection B, between A and B. So that's this section right here. So this is A and B, right there. And then the next part is A intersection not B. So not B is everything outside of B. And then, of course, A is anything inside here. So the overlap of my squiggly circle and the straight lines is this section right here. Okay, the overlap there is not part because that's not part of my squiggly circle here. It's inside B. All right, so what that means is exactly what we can see is that the circle of A is equal to the union or the combination of A not B, A intersection not B, and A intersection B. So that's the first one shown. Okay, the second one then says A intersection B and A intersection not B are mutually exclusive. That we can see here as well because there's no overlap between the green and the blue, right? That's what mutually exclusive means. Mutually exclusive means that there's no overlap between the two, that they can't possibly overlap, which makes sense anyway because we know that it can't be both intersecting B and intersecting not B at the same time. Either it's B or it's not. It cannot be both. And so again, using our Venn diagram and using our logic, we can check that one off, saying that they're mutually exclusive. The next step says that the probability of A is equal to the probability of A and B union A intersection B. Well, that one is really just an algebraic step because we've already shown that A is equal to A intersection B union A intersection not B. Right? So that's just the number of occurrences there, right? And if I divide everything by the total number of items, because this is just saying there are X number of items in A. This is saying that there are X number of items in A intersection B union A intersection not B. And so if I just divide both of those by the number of items in the full set, then what I get is the probability. And so therefore, I think usually they call this a property of equivalence or an algebraic, or you can just say by algebra, we divide both sides by the total number and we get the probability of A is equal to the probability of A and B union A and not B. All right, so we've now shown step 3. Now in step 4, it wants us to change this up just a little bit. Okay, the first thing, if we're looking at this, right, you can see the probability of A and not B there, which is kind of here, probably A and not B here. So the first thing that we're going to do is we're going to say, well, because in step 2 here, we showed that those two things are mutually exclusive, then we're going to use the probability. So we're not really going to go back to the Venn diagram here. I know the question says using the Venn diagram, but we've used the Venn diagram to show the first 2 or 3 steps. And so because we've done that now, we are using the Venn diagram if we use the laws of probability here. And so what we're going to do is we're going to rewrite for this 4th step here because I see that A and B not B there, and I want to have add them, I'm going to recognize that because these two are mutually exclusive, that means that the union of these two things is the same as saying the probability of A is equal to the probability of A, I don't need that, A and B plus the probability of A intersection not B, right? And you can, that's in your formula packet. Hopefully you've used that a couple of times over the last day or two, but that is in your formula packet, that for mutually exclusive events, that the union is the same thing as just adding those two together, right? So we've used that property or law of mutually exclusive events to rewrite it this way. Now, this is another place where I believe that this was not a well-written question, because the last step is now going to assume that these two things are independent. So I'm going to make a caveat here, and I'm going to say if A and B are independent, then we can use the law of independent events, which allows us then to say that this doesn't change, but PA intersection B is the same thing as PA intersection PB. All right. And again, I really don't like the way that this question was written, because it asks us to do this, and it also asks us, sorry, I wrote an and there. This should be multiplication. No, I won't do it. Okay, so multiply by PB. So number one, it asks us to use the Venn diagram to show these things, and we don't really use the Venn diagram here. We're using the laws of probability. Most of the laws of probability we did kind of show or prove using a Venn diagram, but not necessarily this one. They want us to use the Venn diagram in the first steps in order to be able to use our laws of probability in conjunction with the Venn diagram in order to be able to prove the following steps. All right, so we're not really going to use a Venn diagram here. We already used it to prove the first two steps, which then led us to this conclusion, and that's how we're using the Venn diagram. Again, my second problem is that it doesn't tell us anything about the two A and B being independent, but in order to answer this question, you have to make that assumption, which is an assumption you should never make. So, given that, we're going to write that down. If A and B are independent, then this statement, this fourth statement here, is true. All right. Now we're going to go ahead and move on to the last one. Hence, probability of A intersection not B is equal to probability of A times 1 minus the probability of B. All right. Now, so in this case, what we need to do is we are going to take this piece right here, and we're going to move it over to the other side. Why would I do that? I don't know. No, I'm just kidding. Why would we do that? Well, because we see in this question that it gives us the probability of A intersect not B. So that needs to be by itself. So let's solve for that and then see what needs to happen from there. So what we get here is the probability of A is equal to, not equal to, minus the probability of A times the probability of B is equal to the probability of A intersection not B. Now, because these both have the probability of A, we're just going to factor that. Remember, probability of A, probability of B, they're just numbers, right? 50%, 30%, 27%, whatever it is. So if I factor that out, I'm left with a 1 minus PB. And that, my friends, is exactly what we're looking for. Okay? So we've now shown that this is true if A and B are independent, right? So this still hinges on that A and B are independent. Now, because we have this, right, 1 minus PB is the complement of PB. So this is really PA times P not B is equal to P A intersection not B. Now, if this is true, right, this is our independent law. So if we're saying that this is true because we've worked it out through our algebra, if this is true, then what it means is that A and not B are independent of each other. So basically what we've done is we've gone through and made a proof using the Venn diagram and laws of probability. And our proof says if A and B are independent, allowing us to make this step, then A and not B are also independent, okay? Which stands to reason. However, at the same time, in mathematics, we don't really like deductive proofs. We like to be able to prove mathematically or algebraically that something's the case, and that's what we just did. So I hope that video is helpful for you. See you later.